Okay, today we'll discuss about another chapter, that is mechanics of solids. Okay, so this mechanics of solid, this is otherwise known as solid mechanics, or in engineering they called it as mechanics of materials, or they call it as strength of materials. So whichever way you want to tell. Okay, it can either be like in your 12th, they call it as solid mechanic properties of solids. In your chapter, they are telling properties of solids, or this is mechanics of solid, or solid mechanics. In engineering, we call it as strength of material or mechanics of material, whichever way you want to tell it. Okay. So I'll not get into all the theory behind it. I'll just touch upon the important formulas, like using which you can solve some numerically. Okay. So first we'll start with stress and strain. Okay. So stress and strain. So what is the formulas for stress and strain? What exactly is stress and what actually is strain? Okay, so you can see here, this is a rod. Okay, so this is a rod where you are applying some tensile force. Okay, so you are applying tensile force. So the force will be compressive. If you apply the load like this, it will be compressive. Right? There are two forces. One is tension, one is compression. So when you apply compression, it will come to this condition. Okay, so it will get compressed by a distance del and because of compression. So compression, the length will decrease, and the tension, the length will increase. Okay. So I just taken an example, this red one. This is a rod of length L, small l, when subjected to tensile force F, get extended by a distance delta L. Okay. So if that is the case, if you take the cross section, or if we see from the side, it is a circular area and the diameter of this rod is D. So area of cross section is pi by 4 D square. Okay, so strain is equal to change in length by original length. So what is the change in length? Delta L. What is the original length? Length L. Okay. So the unit of delta L is mm. The unit of L is mm. So mm by mm means it becomes unitless. So strain is unitless. Very important thing. And other thing is stress. Okay. So you say that when exam is nearing, I am under stress. Okay. When I think too much about something, I am under stress. So here in solid mechanics, what is stress? Okay, that I told the literal meaning of stress. So you are applying some force. Okay, it is getting elongated. So inside the material there are some molecules. Okay, they are attracting each other. Okay, so that's how. So the I was telling about the different types of molecular force. So the molecular force is very high in case of solids. In liquids, it will take the shape of the container. So the molecular force is still less. And in gas, the molecular force is very less. Okay, so here, because of this force, the molecular distance, the intermolecular distance will increase, and after all, there will be increase in length. So, because of that, when you are stretching something, that rod will be under stress. Okay, that rod will be under stress. So, so you are applying a force F, cross-sectional area A. So, stress is equal to force divided by area. Okay, and force, what is the new unit? Newton. So, in SI unit or in MKS unit, we know three units mostly: SI, MKS, and the CGS unit. Okay, M stands for meter, K stands for kg, S stands for second. Okay, in CGS, similarly, C stands for cm, G stands for gram, and S stands for second or whatever. So we hardly use CGS unit, we use MKS unit or the corresponding SI unit. And there is a unit called FPS unit, which is foot, pound, and inch. That is used in US. So if you go to US, in US they tell everything in terms of foot, inch, and pound. But in UK, in Europe, if you go, it is Newton and meter, second, that kind of unit they will use. So so US they use FPS unit, foot, pound, second. Okay. So this stress is force by area. Okay. So force unit Newton. So what is Newton? Newton is the amount of force required to create 1 meter per second square acceleration in 1 kg body. Right. So 1 Newton is equal to 1 kg into 1 meter per second square. That is the definition of 1 Newton of force. Okay. So so the unit of Newton is kg meter per second, sir. So don't no need to enter into it. So because that's how you get the dimension of Newton. So why we need that? You need dimension. So what is the dimension of a force? Force dimension is nothing but kg meter per second square. So mass, then distance divided by time square, right? Kg is nothing but mass. So your dimension is m l t to the power minus 2. That is the dimension of force. Anyway, not entering into it. So stress is equal to Newton per mm square. So this Newton per mm square is otherwise called as MPa. Okay, 1 Newton per mm square is 1 MPa. That is very important. How? Because you know 1 Pascal is equal to 1 Newton per meter square. Okay. So 1 Newton, then meter. 1 meter is equal to 10 to the power 3 mm. Then you are squaring it. So it becomes 1 by 10 to the power 6 Newton per mm square. So 1 Newton per meter square will be 10 to the power 6 into 1 Pascal. So 10 to the power 6 into 1 Pascal is nothing but megapascal. Megapascal. Okay. So Newton per mm square is nothing but megapascal. This is very, very important in all our engineering problem. We say 1 Newton per mm square is equal to 1 megapascal. 1 Pascal is equal to Newton per meter square. Understood? So this is what the formula for stress and strain. Okay. You can take a picture of it. We'll get to the next. Okay. So 1 Newton per mm square is equal to 1 megapascal. Unit of stress is nothing but Newton per mm square. Unit of strain is unitless. So strain is unitless. Okay. So in softer material, the strain will be more. If the harder material, the strain will be less. So like say if you so in softer material the strain will be more. In harder material or stronger material the uh, strain will be less. Okay. So you imagine this is a rubber. Okay. You imagine this particular rod is a rubber. Okay. If it is a rubber, the strain will be more. If it is aluminium, the strain will be little less. But if it is steel, the strain will be still less. Stronger material under the application of the strain, same force, stronger material, the strain will be less. Stronger material, the strain will be less for the same force. But softer material, the strain will be more. Okay. So aluminium is considered to be comparatively softer. It will take more strain as compared to steel or the other material. Okay. And harder material, there will be hardly any strain. Like say very hard material, like the diamond or whatever, it will break. If you apply a force, it will break. That is called brittle material. Okay. There are different types of material. Something is called ductile material. Something is called brittle material. So ductile material will allow like there will be certain amount of strain you can create in ductile material. But in brittle material, if you apply force, it will break. It will not elongate much. Okay. So now we'll get into the concept of Young's modulus. Okay. So now you know that unit of stress is Newton per mm square. Unit of strain is unitless. So we have taken an example of a rod under tensile loading, and then we found out the F by A is stress, change in length by original length is nothing but strain, and then we'll find out what is Young's modulus. Okay, so what we have studied here is nothing but your tensile strength. Okay, and okay, before moving into the Young's modulus, so we have studied about tensile strength. We have studied about tensile strain, stress tensile strain. We have studied tensile strain, which is nothing but delta L by L. Okay. There is another thing which is called the shear strain. Okay. So what is shear strain? Shear strain. So here what is in tensile strain? Let us say it is fixed at one end. If this is a rod, you are applying a force. This is cross-sectional area. This cross-sectional area is A. So this and you are this is your length. This is your change in length. So this is your tensile strain. And tensile is nothing but your delta L by L. Okay, so this is tensile. So what is shear? So in this case, you are applying the force perpendicular to the area of cross section. When you apply a load perpendicular to the area of the cross section, that is called tension. Okay. What is shear? When you apply a load parallel to the area of cross section, that will cause shear. Okay. So we'll have one example. Let's say you have a cylinder. Okay. Let us say you have a cylinder. Okay. So you have a cylinder. Okay. So this cylinder, let us say the length of cylinder is L. Okay. So the length of the cylinder is L. Okay. Now you apply some force. You apply some force parallel to this cross section area of the cross section. See here you are applying perpendicular to the area of cross section. Clear, na? Yes. Like see this is my area, and I am applying the load perpendicular to it. So in this case, but here your area of cross section is this one. Okay. You are applying a force parallel to it. Okay. So you are applying a force parallel to it. Okay. So when you apply a force parallel to it, and it is, let us say it is fixed at the bottom. It is fixed at the bottom. Right? So after, because of this shear force, there will be some amount of deformation. Okay. This is before and after what will be the situation? After applying the force. So this line will get inclined by some amount, and it will be inclined by some amount. So it will look like this. Okay. So let us say this line got deformed by some angle theta. Okay. So this got deformed by some angle theta. Okay. It got deformed by some angle theta. So this is the force you are applying. That is the force parallel to the cross section. Okay. So let us say this distance is this from the original position. It has moved by a distance of delta x, and the length is L. Okay. Okay. So what is the shear? So a load applied parallel to the surface cause shear stress or shear strain, right? So we have so this is tensile strain is otherwise called as longitudinal strain. Longitudinal strain. Okay, right. So this is shear strain. So what is the formula for shear strain? Okay, so this shearing strain formula strain is equal to formula is actually here it is del x by L. Del x means this original line has moved by a distance del x and the total height of this cylinder was L. Okay, this is otherwise called del x by L. Okay, so this is otherwise this is tan theta, right? Why tan theta? Because in trigonometry you have studied like if this is my right angle triangle, so if this is theta, okay, and if this is delta x and if this is L, then my tan theta is equal to your height by base, right? You in trigonometry call it as height, you call it as base, and then this is called as
hypotenuse.
which one is called this?
That is perpendicular.
This one is hypotenuse.
No,
this line.
that is hypotenuse.
And this what we call
Perpendicular.
means P. P and this thing. Okay. So tan theta will be P by P, right? P by P. That is what in trigonometry you have studied. In this case, same things applies. This is your length L. This is your length L. And this is your delta x. So this angle is theta. Okay. So if you take tan theta is equal to del x by L. You can correlate these two. You are able to correlate. This is because this is a right angle triangle. This is a vertical line. This is a right angle triangle. So if you magnify it, it is something like this. This is a right angle triangle. This is this and this is this. Right? This is your theta, and so this is your delta x, and this is your L. Now clear? So this tan theta, the shearing strain is equal to tan theta. Tan theta is equal to your del x by L. Right? So limit, there is something called in your limit derivative before derivation and integration you have studied limit. Okay. So limit tan theta tends to 0 is equal to theta. Okay. So this tan theta or del x by L, because this is very infinitesimal, a small angle. So your shear strain is nothing but your tan theta or theta. Okay. So now you understood what is tensile strain or longitudinal strain and what is shear strain. Okay. Similarly, there is something called volumetric strain. Okay. So volumetric strain, three strains we will study. One is longitudinal strain, one is shear strain, and then another is volumetric strain. Okay. So that volumetric strain. So this shear strain, another example is your book. Okay. So let us say your book. A very good example of shear strain is your book. Okay. So this is your book. You are holding. This is your book. So let us say you apply some force on this book parallelly, like this. You can see it has shear. Earlier it is perpendicular line. Now you are applying a force parallel to the surface of the book. So can you imagine this line which was vertical, now it has become inclined. This has become inclined. So the angle it makes with the original vertical line, that angle is the shear strain. Okay. So you are applying the force. How you are applying? You are applying the force. You are just holding it, fixing it, fix. Then you are applying the force on the surface of the line. That's why it is called shear. When you apply a force parallel to the surface, that is called shear. So here it is getting sheared, right? So when you are, suppose you are chopping it, you are chopping some vegetable, that is shear, because you are chopping it up. So the force you are applying is a shear force. You are cutting something by your scissor, that is also shear, right?
Yes.
Because that is applied parallel to the surface. Okay, you are chopping vegetable, you are cutting something by your scissor. That force is applied parallel to the surface. That's why that is shearing. Okay. So we have studied about longitudinal strain, and we have studied about shear strain. Then we'll study about volumetric strain. Okay. So let us imagine we have some kind of volume. We have some kind of volume like this. Okay. So now on this volume, I keep on applying some pressure. Like I apply some external pressure. Okay. I apply some external pressure. So I apply some external pressure. So under this external pressure, the initial volume get deformed to this condition. So my initial volume is the blue one. My final volume is the red one. Okay, because of external pressure. So the volume gets changed here. Okay, let us say the blue one, the volume is V. Okay, and the change in volume is delta V. You can imagine more in case of a sphere. So you have a sphere, you are applying some external force here on the sphere, okay, and your sphere get the original condition, the new condition will be something like this, okay. So your sphere uh, initial volume is V. The change in volume is, let us say, the volume initial Vi, volume final you can say Vf. So delta V is equal to Vi minus Vf. Okay, Vf. Okay. So there is a change in volume. So volumetric strain. What is the formula for volumetric strain? So volumetric strain is equal to delta V by V. So this delta V, that change in volume, and in the denominator it will be always original. Okay. Whether it is shear strain, whether it is longitudinal strain, in denominator it will be the original. Change in length by original length. Change in distance by original height. Change in volume by original volume. So that is strain. So on in the denominator, always the original value will be there. Okay. So now we have learned about three different strain. Okay. Uh, we have learned about three different strain. Now we'll get into Young's modulus. Okay. So you can take a picture of it. We'll go to the next this thing. So what is Young's modulus, and maybe before that talking about the stress strain curve. So we'll draw the stress strain curve, and we'll tell what is Hooke's law, and okay, we'll discuss about Hooke's law, and we'll discuss about the stress strain curve a bit. Then we'll get into the Young's modulus, shear modulus, uh, or the rigidity modulus, or then we'll get into bulk modulus. Okay. Okay, so we'll get into it in the. So we'll just give an introduction on the
Young's
Young's model. So we'll study about the stress strain curve in the next class. Here we'll just I'll just introduce you what is Young's modulus, so that there can be n number of numerical related to Young's modulus. Okay, so Young is the name of a scientist. Okay, so he found that Young's modulus is a property of a material. So more stiff is the material, more is the Young's modulus. Okay. So we'll discuss about the stress strain curve in the next class, but at least we'll give an introduction to Young's modulus. Okay, so Young's modulus is something related to tensile behavior. Similarly, there is something called shear modulus. Okay, shear strain by shear stress, or shear stress by shear strain. Okay, so what is Young's modulus? Young's modulus, or otherwise it is called modulus of elasticity. Young's modulus or modulus of elasticity. Elasticity. Okay. So what is this? This we denote it as some in some book here in your book they are identifying it as Y. Somewhere they call it as E also. So after the scientist named Young, they have defined it as Y. So Y is stress by strain. So I have introduced stress to it, force by area. Okay. Stress is called sigma, which is force by area. Right? We have defined strain. I am talking everything with respect to longitudinal. I am not entering into shear or bulk modulus now. So this is change in length by original length. So what is Young's modulus? Y is equal to stress by strain. Okay. So what is Y? It is F by A divided by delta L by L. That is your Young's modulus. Okay. So the unit. So unit. The strain does not have unit. Yes. So Young's modulus unit is same as Young's modulus unit is same as unit of stress, which is nothing but your MPa or whatever. Yes. So Young's modulus unit. Okay, so this is so in the next class we'll study about the stress strain curve and all. So just to give you some properties of this material. So as I told, a stiff material, right? What happened? So when I say Young's modulus is high, what does that mean? That means the numerator, if the numerator is high and the denominator is less, then only Y will be high, right? So for more stress, if you are causing less strain, that means Young's modulus is high. So here, A is anyway constant. L is anyway constant. So you are not applying stress, you are applying force. You are not you are causing strain, but in turn you are causing change in length. So otherwise we can say that for a material, if you are giving more force to which cause less deformation, for more force, if you cause less deformation, that means Young's modulus is high. Yes. Okay, more force, less deformation. That means steel is a stronger material. Its Young's modulus will be high. Aluminium is a softer material. Its Young's modulus will be less. Because for aluminium rod, you will apply more force, you will get less. You will apply less force, more deformation. So for aluminium, if you compare aluminium with steel, okay. So for aluminium with less force, you can get more deformation, right? See, for steel with more force, you will get less deformation. Okay. So if numerator is less and denominator is high, your Young's modulus will be low. Yes. Right? Because and here Young's modulus is high. Right? So this is how a softer. So if you consider rubber, Rubber is Young's modulus is much lesser as compared to aluminum also. With very little force it will get extended. So, but one catch here. So, somebody will ask you rubber is more elastic or steel? The answer is steel because its elasticity is more. So, one gets confused there. So, Young's modulus of steel is much more than the rubber. That's why it's this thing. Okay. So, we'll take some example of some different values. Say, let us say we draw a table. We will draw a table and different material. Let us say we have density here. We have density. Okay. Then we have Young's modulus here. Okay. Then we have something called strength. That is the stress. Suppose ultimate strength. What is that? At some point it is going to break. At that point, how much stress it can carry. That is called the strength or ultimate strength. We'll study that actually. So in the stress strain diagram, you might have seen something like this. So you have stress here, you have strain here. So this maximum stress it can carry is called ultimate strength. Okay. So that is called ultimate tensile strength or UTS. Okay. And then you can have a yield strength also. Yield strength. Yield strength. Okay. So then your substance. Okay. Substance. So like this, you can make a table. Okay. So you have aluminium, Al, you have copper, Cu, and then you have steel, you can say Jp or whatever. And then you have glass, and then wood, bone, and then polyester, which is nothing else. Okay, so aluminium, what is the density? Aluminium density is 2710. Unit of density is kg per meter cube. Why? Because density is mass per volume. Mass per volume. Okay, so mass is kg, volume is meter cube. Right? Right? So aluminium density is 2710 kg per meter cube. Why? Because you always you think about water. 1 meter cube of water will have weight 1000 kg. So density of water is equal to 1000 kg per meter. Okay. So density of aluminum is more than that of water. Very obvious, that is liquid, this is solid. So density of aluminum will be more than that of water. So this 2710, we otherwise called something called specific gravity. So the specific gravity of aluminum is 2710 divided by 1000. That means density of aluminum divided by density of water is called specific gravity. So this is called specific gravity. So it is the density of any material as compared to water. So water, so if you just remember aluminum specific gravity is 2.7, you just multiply 1000 with it, you will get it in kg per meter cube. So water 1 meter cube means what you imagine. So you think that let us say this is 1 meter. Okay, it is not square, it is rectangle. Another area 1 meter you imagine. This side is 1 meter, this side is 1 meter. So this is 1 meter square, and in the length direction 1 meter you go like this. Okay, so that container of length 1 meter, breadth 1 meter, height 1 meter, whatever water it can contain, that will be the water contained in 1 meter cube container. That weight will be 1000 kg. Okay, so that is the meaning of 1 meter cube, like a cube of side 1 meter, a cuboid of side 1 meter. So 1 meter cube will contain 1000 kg of water. So that is the meaning of 1000 kg per meter cube. That means for volume of 1 meter cube will contain 1000 kg. Okay. So 2710 is the density of aluminum. For copper it is 8890. That means copper specific gravity is 8.89. Okay. Then steel Steel is 7860. Steel I have put iron because steel is a alloy of iron and carbon. So major constituents of steel is iron and carbon. Then you can add other alloying element like tungsten, like chromium, depending on the requirement. Sometimes you use steel for cutting tools. Sometimes you use for structural application. So depending on the requirement, they will produce different kind of steel. Okay. So this is iron. Then you have glass. Glass is 2190. Okay. So glass has lesser specific gravity as compared to aluminum. Okay. Then polyester, which is something closest to the plastic. So its value is 1053. Just we need to remember we don't have to buy heart, but we need to have a feel of it. Just remember that steel is 7.8 times heavier than water. Aluminium is 2.7 times heavier than water for the same volume. That is the meaning of that. Okay, then what is the value of Young's modulus? So steel has Young's modulus. So this Young's modulus is in like it is given in GPa. Okay, gigapascal. Okay, giga is 10 to the 9. Okay, so that value gigapascal. So aluminium is 70 gigapascal. Okay, and steel is 200 gigapascal. So and then copper 110 gigapascal. Okay, so you can see here among all, and you can see iron will have lesser strength as compared to steel. Okay, iron will have 190. So iron and steel are different. Anyway, and not entering more into it. So just see aluminum is 70 gigapascal, whereas steel is 200 gigapascal. Gigapascal. So stress, when you come to strength, it will be in megapascal. But your Young's modulus will be in gigapascal. Why? Because Young's modulus will have stress divided by strain. So this strain is always very less, 0.001 or something like that, which is nothing but 10 to the power minus 3. So in the numerator you have 10 to the power 6 and you are multiplying 10 to the power 3. So mega becomes giga. Because your strain is like 0.001 or something, very little, very small. That's why that stress, the strength we measure in mega, whereas your Young's modulus you measure in giga. Okay, that's the difference between mega and giga. Okay, and then this is in giga, whereas this ultimate tensile strength is in megapascal. Okay, so you can see aluminium, it is 110 megapascal. Whereas your steel, it is something around 400 megapascal. So steel is more stronger. Steel has better Young's modulus. All that. Okay. So that is one. And then yield strength is always little less than the ultimate strength. So you know this point is yield. We'll study that. This point is yield, and this point is your ultimate. Okay. So this is yield and this is your ultimate. This point, at this point, the highest load it can take is ultimate. So it is strength, but actually you are applying force. This is strain, but actually the change in length is what you are measuring. So this you are applying and this you are measuring. Length remains same. Even though it is del L by L, actually you are measuring del L. Even though it is F by A, actually you are applying force. So you are applying this, you are getting this result. So this is the action, this is the result. Okay. So the ultimate tensile strength is 110, right? So then yield strength will be little less than this because this is below this, right? So it is something like 95 here, and for steel it is 250 or whatever. So you can got a feel of this values. So when normally they say that we should not remember anything, we can refer everything, but that is not true. You should remember some values so that you will have a feel of it. At least you should remember aluminium Young's modulus is 70 GPa, steel Young's modulus is 210 GPa. That's all. Then specific gravity, aluminium specific gravity is 2.7, steel specific gravity is 7.8. This you should remember to have a feel. as compared to water, how heavy it is. Okay. So similarly, ultimate tensile strength and yield strength. These values you should remember to have a feel. Okay. So we have discussed about Young's modulus. Then we'll discuss about the stress strain curve in the next class. We'll study about the shear modulus. Then we'll study about the bulk modulus and how these three modulus are interrelated to each other. So this Young's modulus and bulk modulus and shear modulus, how they are related to each other, that also we can discuss. Okay. Okay. We'll take it up in the next class. Okay. Thank you.